introduce you, Valeria. Okay, so now we are recording. So welcome everyone. Thank you for joining us. My name is Daniela Grandon and I'll be your host. It is a pleasure to have with us Valeria Pettorino from CosmoStat group at CEA-Saclay. Valeria holds a PhD from University of Naples, Federico II, and her research interest is cosmology and astrophysics at the interface between theory and observations. Today, Valeria is presenting dark energy from theory to data. So thank you, Valeria, for accepting our invitation, and you are free to start.
Thank you very much. I put the timer. Actually, I forgot to. Okay. Thank you very much for the invitation. It's a pleasure to even be remotely here. And yeah, I'll be talking about dark energy from theory to data. Since actually, well, I know some of the people in the audience, but I don't know if you know me. So I'll also say something about me, about myself, about the group where I'm working on now, CosmoStat. And then I'll tell you something about recent work that I've been doing, a bit on the theory, a bit on statistics, and a bit on observations. I hear some noise. I don't know if perhaps you can. Okay. So first, I'll start with me. As you were saying, I'm a physicist and I work on cosmology. I've worked originally mainly on theory as a theoretical physicist on dark energy, modified gravity, CMB, neutrinos, and then more and more with years on data. I hear lots of noise.
Yeah, we're trying to see who's, yeah, now it's muted. Valeria, you're muted. Daniela, you're muted.
Yeah, sorry. Valeria, can you turn on your microphone, please?
Or maybe
Valeria, can you hear us?
we cannot hear you.
Yeah, the thing is that
Okay.
if I share, I don't see anymore the Zoom.
Yeah, sorry. Yeah, sorry. So, okay, that's good.
I restart. Okay. Here. Okay, so I was saying I worked on the Planck collaboration now since 2009 until last year. And since 2007, I'm also in the Euclid collaboration. I'll tell you something about that in the last part of the talk. Actually, there's also Domenico, who is one of the core team members in the INTERSCIENCE task force where that I'm co-leading within Euclid. And in general, as you said, I got my PhD in Napoli, then I lived in different places, and I'm now at CEA in Paris-Saclay at the Department of Astrophysics since 2016. I, in general, try to say I'm interested in things that, let's say, go a bit at the interface between theory and data, but also across different topics. And so I've been engaged in different networks, either on, for example, Python, or on data science, or within networks in which actually I think we also have one of the mentors here, Bernardita, for Women in Physics, which is the Supernova Foundation, which perhaps some of you are aware of. And also we are still trying to organize a school on cosmology that we've been organizing for 14 years, which is in Italian Alps, and that now registrations are open. And it's supposed to happen in presence, if possible, in December. We'll see. So let me say something also about CosmoStat. CosmoStat is the group where I'm working on now, and it includes several people. It's about 20-25 people who have different expertise, partly on cosmology and partly on statistics, so on weak lensing mainly, but also on CMB, galaxy theory, different aspects. And on signal processing, there's lots of people who are expert on machine learning, compressed sensing, optimal transport, also within applications outside astrophysics and in with collaborations with the neuroscience department. There's a website where the group has made available 39 software packages that you can find and download here. And especially now during the pandemics in the last year, we have opened a YouTube channel where we publish tutorial sessions for scientists, mainly based on different topics, either on software development or also on communication, on science, and so they're also available on this website. There's actually some hyperlink here, but I mean, you can go to the CosmoStat webpage and they're accessible from there. So within this talk, I'll reference some of the works that I summarize here that were done, of course, thanks to many other collaborators. On the theory, in particular with Adria Gomez-Valent and Luca Mendola, on the statistics, mainly with my current PhD, Virginia Ayani, Austin Peel and Jean-Luc Stark, who are at, well, Austin was a former postdoc at CosmoStat, and Jean-Luc is again, the lead of the CosmoStat group. And then collaborators, many, I just mentioned here one, but I mean, there's many in Planck, in Euclid, in particular Matteo Martinelli, who's former postdoc, and Santiago Casas, currently postdoc also at CosmoStat. And some of these papers also reference simulations that were done with different collaborators, in particular with Marco Baldi. So let's start from cosmology and from the standard model, where, well, as you know, it's currently, the universe is currently in an accelerated expansion phase, although we don't really know what causes this cosmic acceleration. And also, we don't really know what's in it, what's inside the universe. The matter part that we see is just a small fraction of the total density, and we don't know what's the rest that makes it the universe. That's enough for the universe to be spatially flat, and that still justifies this accelerated expansion. One possibility is to have a cosmological constant, so a constant contribution in time and space, which adds to roughly 70% of the total energy budget. But is that really a constant? So it is indeed a parameter that currently fits the data. And I think that actually was not trivial in the sense that it still is a good fit to the data after many data sets, many tests, independent tests from space, from ground. So it was not obvious that it would have resisted for so long and that would still match all these data sets up to now. Still, it does not really match theoretical predictions. It requires extreme fine-tuning. It marks the present epoch as a very special time in the evolution of the universe, which is also why many people for many years now have tried to test other proposals beyond the cosmological constant. So to see whether whatever causes cosmic acceleration is rather due to a dynamical contribution, something that changes in time and space that could be interpreted as a fluid, to which usually we refer as dark energy, or more in general as a force, a modification to gravitational interaction as we know it from in the standard framework in general relativity. And ideally, we would like to test particle and forces in cosmology. And so interactions at cosmological scales as we do in particle physics. Also thanks to the complementarity of different probes at different scales and at different epochs. There's many questions that we can ask, but there's different questions that we can ask. And two of them are here, which I think are, again, still open questions nowadays in cosmology, and that they might, I mean, I stress that they're different because they may require different strategies in order to actually answer them. So first, we want to understand whether we can falsify the cosmological constant, and then we would like also to know whether we can distinguish among its alternatives. Again, if a cosmological constant is actually falsified. So depending on which of these two questions you may want to ask, you may have, again, different strategies. Strategies that might involve usually three different, let's say, tails that are there for the same quest. On one side, you could, as a theorist, you can work on theoretical models. You can try to think about new ideas, develop new theoretical models, which have to be convincing already, I mean, theoretically. They need to be tested, and they need to match at least all the data that are available up to now. You can work on the methodology, in the sense that you can make sure that your data analysis is optimized, that you're using numerical codes which are reliable, that you're aware of testing, for example, different statistics, and all these choices also somehow have an impact on what your final result will be. Or you can try to look for more data, for more frequency coverage. You can look for independent probes from the sky, from ground, and compare them. And at the end, I think it's important, on whichever tail you are in, to be aware that each of these blocks somehow involves questions and choices that might have an impact on the other. Sometimes it's not always trivial to understand what are the assumptions done in all these aspects, but again, I think it's good to be aware, at least to have a feeling of what's happening in order to, again, because they all contribute at the end to the same quest. So I'll start from theory, but in particular from something that I've been working on for a long time, but that we recently updated in this paper here. But that I mean, I've been working on coupled dark energy for already in the past. So usually on the theory side, there's two main strategies. Usually you can start from an action, you can start from a specific cosmological model, and there's many that, I mean, you could consider, and then you calculate all the equations for the background, for the perturbations. You try to estimate your predictions at nonlinear scales, and then you compare them to the data, and you check whether they match or not, the fit or not the data. And this somehow replies more to the second questions I had before. So to which is the actual true action, the actual model that describes the world, the universe. The second one is a more phenomenological approach, which can, for example, rather start from functions of the perturbations, and these mainly usually try to disprove lambda CDM. For example, if you have in mind those mu or eta or sigma functions, those functions of the gravitational potentials that describe the metric. And these ones basically would be, for example, one in lambda CDM. And so if you check, if you manage to test them with respect to one, then you would be able to, again, disprove in principle lambda CDM, but it's harder to then connect them to what's the actual truth model that describes cosmology. So in this sense, they answer different questions, and they have therefore different objectives, which, however, again can bring complementary information. Coupled Drake energy falls into this first case, in which you start from an action, and there you have usually Lagrangian, where there is let's say the mass of dark matter particles that depends on a scalar field, so it's not constant. Dark matter particle interacts, and the interaction is mediated by a scalar field that also causes cosmic acceleration. So this introduces a force that modifies gravity. In the simplest model, it in practice adds a constant term. This beta is the strength of this interaction, and in the simplest case, it's a constant. So we have updated constraints of this model, this set of cosmologies, with all the current data which are available recently in this paper. One interesting aspect that we wanted to check also while updating constraints was how or whether it can actually help with H0. This actually, we had already somehow proposed this or looked into this many years ago, before there was even any tension in the Hubble, let's say, related to the Hubble parameter. But we wanted to check this again with the updated data also, I mean, after some claims in this direction. So you may know, probably you know, that there is currently a tension between CMB probes and direct measurements from supernova, in the sense that the value from H0 from Planck, for example, is lower than the one you get from direct measurements, for example, from Schuss and Rees et al. Not all of these are independent, so you can't actually combine all of them. But I mean, this is one example of plot, and I don't want to describe here now all the data. There is a review of data that you can find here, and the recent review of theories that claim that can address this in here. What I was looking for was mainly to update the coupled dark energy constraints to see if it's still compatible or not with current data, and it actually is. And the point is that if you look at the matter power spectrum for different couplings, the effect of the fifth force is basically the fact that you are enhancing the growth of perturbations at again in the basically nonlinear regime. And this effect is degenerate with the effect that neutrino masses have. So once you know this, once you have you know the physics, and then you have an expectations, and then it's actually not so difficult modifying a Boltzmann code to produce, for example, 3 models, one of which is lambda CDM, and other 2 in which you have a strength of beta, of different strength of the coupling, and the different values of the neutrino masses. Because in practice, I'm just playing with this degeneracy. Still with neutrino masses, which are compatible with the values that we have, and also with spectra, which for the same values of the parameters can give me a CMB and a matter power spectrum that is still basically fine and compatible with the data. The fact that it's compatible is actually seen, of course, through a Monte Carlo, but I mean, I just wanted to show that already, even just looking at the observables, you can imagine, I mean, why this happens. So the actual analysis with the Monte Carlo analysis is again updated into this recent paper, where separately we have considered the effect of each of the data sets. So the comparison with each of the data sets, always along the line of thinking that it's never a good idea to combine lots and lots of data because you never know what is driving which result. Okay, so basically here what we see is that we do find some peak corresponding to a coupling which is larger than 0. But let's say this really depends on which data sets you consider. And I wouldn't say, so for example, if you include, if you combine Planck and Schuster and Holy Cow, then you get the largest deviation. But I mean, I don't consider this, let's say, as statistically significant, let's say, to say that there is evidence for a fifth force. Still, it's compatible with the data that we have so far, and it's partly degenerate the strength of the fifth force and the expansion parameter. Also, when you actually use a model selection criterion, which is based on the full Bayesian evidence, then lambda CDM is anyway preferred, even in the red case here, because you penalize the model that have an additional cosmological parameter with respect to lambda CDM. One interesting aspect of these models was also the fact that it belongs to the set of models which is called, which is a force accelerated model. And this is a concept that we had introduced 2 years ago with Luca Mendola, because we were thinking of, I don't know if, I mean, probably some of you heard of the concept of the self-acceleration that was kind of popular for a few years, that originally was motivated in order to distinguish what is genuinely a modification of gravity, so something related again to an interaction, to a force that is modified, with respect to having a cosmological constant hidden, for example, in a potential. And although the motivation, the original motivation, I mean, can be interesting, in practice, the definition had some issues that we highlighted in this paper, in the sense that it could not be applied to universal coupling. It could only be applied to universal couplings, and it was also too narrow in the sense that it was excluding more models than the original motivation would have wished for. So we actually introduced the two new concepts, force accelerated and fluid accelerated models, which follow the original motivation but have different definitions, which can be applied also for models which are not universally coupled, in the sense that different species may interact with different strengths. There's a question, or I hear some.
Yes.
I cannot see if someone is raising their hands because I cannot see the Zoom thing. But
no, there are no hands raised. So Charma, can you please mute your phone, your microphone? Charma, sorry, I will mute again to everyone, and Valeria, you unmute yourself, please, because, no, there it is. No, there it is. Now here's mute. Okay, go ahead.
Okay, cool. Okay, so I was just saying exactly that, then, I mean, in the papers, there's the exact, say, practical definition of how to decide whether, if you have a model, your model is actually force accelerated or fluid accelerated. So in the first case, it would be really a genuine modifications of gravity. In the second, it's rather related to a potential, or in practice, to a cosmological constant. Okay, now as a theorist, especially sometimes when I talk to people that perhaps don't really work on the theoretical side, often one encounters some, let's say, diffidence, perhaps, with respect to exotic models. I have to say that as a theorist, I'm worried about many things, but not about how exotic models are. And the reason is that if we were made of the dark side, if we were made of dark energy or dark matter, of the 96% we don't know, and we looked at the 4% that we actually know, then even there we would find different forces and different particles, different lots of different, again, ingredients. even just in that 4%. And so in practice, this 4%, the 4% of baryonic matter that we know, is much more exotic than any dark energy model or modified gravity model that has possibly ever been proposed. So exotic is not, I think from a theoretical perspective, is not a problem. The problem is rather many other things. The fact that usually when you have a new model, you have complex equations. And so it's sometimes difficult to start from the action and derive all the perturbation equations. It's difficult sometimes to test them, to actually develop Boltzmann codes that need to be modified to take into account these perturbations. Typically, this is left also to theorists to do, not to really software developers. There's very few simulations that can be done or within modified gravity or alternative dark energy models. And so in practice also, even our predictions in the nonlinear regimes for the theoretical part are not as reliable as one could have in lambda CDM, and even in lambda CDM, I mean, it's already difficult. There's often extra parameters, even extra free functions that basically make it very hard to constrain sometimes anything, and also that slow down the whole process. The Monte Carlo analysis can take days, a week to actually be done for a given model. And also, sometimes it's hard to identify as a theorist which are the theoretical assumptions that are already made within the data analysis, unless you actually at some point play a bit with the data or talk to the observers, which is something that I completely recommend to do, because you always discover very interesting things that at the end have an impact also on the way in which you test your theories. So now I'll show you in particular, for example, some of the choices which are instead in the methodology and the statistics that we can use when we compare data and theories. And this is mainly related to some recent work that I've been doing since basically I joined CosmoStat, and in particular with Virginia Ayani. So which one, first, which statistics, which method should I use? There's different ways in which you can analyze the data, and this also has an impact on the final result that you can get. Statistics in general can help you with lots of things. It can help you with when you have missing data, for example, if you have to reconstruct the shape of a galaxy, or it can help with separating the signal from a foreground component, like, for example, we have to do in CMB, in the cosmic microwave background. Statistics can also make a difference to discriminate different models. For example, to deal with that degeneracy that I mentioned you before, the degeneracy between a fifth force and neutrino masses. And I'll come back to that. I want to show you an example later that we considered in this paper. This, of course, introduces new challenges. The numerical challenge, the expertise which is required in understanding which is the actual the system, the statistics which is optimized for what you actually want to do, for what is again your objective, and so this is also sometimes again can make the difference. So I mentioned that again some of this work, most of this part of the work actually is done by Virginia Ayani, which is our PhD student currently. She has a background in dark matter and theoretical models, but then she worked during her PhD mainly on weak lensing and mass mapping. And so she has developed a whole, say, pipeline that I will illustrate in a moment. She is also, like Domenico, a member of the Euclid likelihood team that I'm co-coordinating. So together with Virginia, we have worked mainly on weak lensing statistics. So weak lensing, so on the cosmic shear, so on the distortions of shapes of distant galaxies that we observe from here. whose shape is, again, distorted due to large-scale structure which is present along the line of sight. And what Virginia has done is to develop a pipeline that now goes from the simulations or simulated data, or that can be, again, now we are also applying to data, to real data, calculates the convergence maps from the shear of the simulations or the data, calculates the likelihood analysis that compares the data with the theoretical predictions given a model, and includes also the Monte Carlo analysis to constrain different parameters. If they're simulations, of course, this will be, let's say, forecasts. If they're data, then it will be real constraints on a given theory. And this done for different statistics, different summary statistics that can be gathered from the convergence maps. So one example is in this paper, for example, neutrino masses in lambda CDM using multi-scale peak counts. So going beyond the second order statistics, beyond the Bowie spectra, and going instead to higher order statistics. For this paper, we started from a set of cosmological simulations that include massive neutrinos, the massive no simulations, which are actually quite exceptional in the sense that they're publicly available, and they contain 101 different cosmological models obtained by varying the sum of the neutrino masses. From noiseless convergence maps, we included the noise typical of, let's say, Euclid-like mission to get noisy convergence maps. You then filter them because you want to have access to different scales. There's different ways in which you can do that. In practice, with a wavelet transform, you separate the original noisy map into different maps at different scales. And then you can do different summary statistics on your filtered mass map. Again, starting basically from the convergence maps, filtering. Through this filter, you get what is called the aperture mass map here. And then from this, you can extract the second order statistics, so the variance, or the third order, the fourth order, or you can count peaks. So you can describe the distribution of the local maxima as a function of their heights. That's one possible, let's say, higher order statistics. And then you apply the pipeline, you calculate the likelihood, and you extract your forecast, for example, for a Euclid-like satellite or for another experiment. And in this paper, she compared many different statistics with respect to what you would get for the Bowie spectrum, for different higher order statistics, and also for different filters. So in an ideal setting, if the systematics are all under control, then peak counts actually is the statistics that can perform better in constraining the different parameters that we had available from the simulations, in particular from the neutrino masses and the amount of matter. The actual filter doesn't really make a huge difference, except that it can still let's say, be an advantage depending on what you have to do. But for example, we found that a starlet filter would make the covariance more diagonal, in the sense that only diagonal elements actually are, let's say, are enough to give you the final constraints. And this can be an advantage, not in the final result, but really when inverting the matrix. So it can just speed up your numerical implementation. This is also, let's say, let's say an upgrade of that we had recently published in a letter in this paper, in which we went beyond the peak counts and proposed a new summary statistics, the starlet L1 norm, which is based, it's the sum of the absolute values of the of the coefficients in your, when you expand your wavelet. And in fact, this has the advantage that it avoids the problem of having to define what is a peak or what is a void, because it actually includes the information of every pixel that you have in the map. So we also compare that with pixel on or voids, or with, again, peaks and voids together. So it's actually simpler to compute. It doesn't have the property that, again, your covariance matrix is diagonal. You lose a bit in that, but it's at the end faster to apply. And again, it includes all the information of the map. So in this sense, higher order statistics seems to be a promising way to access, especially the nonlinear cosmological information and the non-Gaussian part, provided, of course, that the systematics are under control. And again, this is somehow to show that depending on the statistics and how you manage to optimize them, then you can get better constraints from your actual data. But also statistics can help in breaking degeneracies. I mentioned before this degeneracy that we know physically is in place when you have a fifth force and neutrino masses. They tilt the matter power spectrum. So we wanted to investigate whether statistics actually can help in that, in discriminating between models. For that, we designed on purpose, so knowing, starting from this known physical degeneracy, we designed on purpose, simulate together with Marco Baldi, simulations that are degenerate in the sense that they include, is done for a universal coupling, so for an F over cosmology, in which in practice you have the same, again, fifth force, which applies in the same way with the same strength to all particles, and massive neutrinos. So for different values of the neutrino masses, we produced simulations in such a way that we knew that basically lambda CDM, for example, was expected to be degenerate at the level of the power spectrum with an F of R model of with an amplitude of 10 to the minus 5 and the neutrino masses of 0.15 electron volts. So we really wanted to produce degenerate simulations in order to understand if there was a systematics that was better suited to break this degeneracy. We then applied again the pipeline. So you calculate, you filter the maps, the convergence maps, you calculate the aperture mass maps, you calculate different statistics, and you get again, you can calculate, estimate different statistics. So here, for example, at second order, if you calculate the variance, as expected, there is the lambda CDM, the gray PDF, which is degenerate as expected with the green one, the one that corresponds to the higher value of the neutrino masses. Because again, you can compensate the strength of the fifth force with the higher value of the neutrino mass. As you decrease the value, then the model, again, the variance gets, let's say, more and more distinguishable from the lambda CDM case. Still kind of overlapped, but again, basically these ones are meant to be degenerate. We tested different statistics, and we noticed that it's actually peak counts among the ones that we tested that were better able to distinguish lambda CDM from F of R models, although they won't help to distinguish among different F of R models. But still, in practice, again, that's a different question. An update of this was published in this other paper here, that was instead trying to use machine learning as a classification problem. So to see if we can actually classify and distinguish these models better. Here you see a confusion matrix. So this means that the rows indicate the true values, the true model, lambda CDM and the three different F(r) models with different neutrino masses. And the columns correspond to your prediction. So in principle, if your method, if your classification is efficient, then your confusion matrix is supposed to be the identity matrix, right? Because your prediction matches exactly your truth. And you see here, even just by eye, that for peak statistics, in the best case that we could find, this is somehow already, I mean, quite good in the sense that you have 66% of probability that your prediction actually matches, distinguishes between lambda CDM and the value, the model which is mostly generous with it. But if you use a convolutional neural network, this actually improves even more. This is even closer. You go up to 90% of efficiency to distinguish your models. So to be sure that you can really detect an F(r) model with a neutrino mass of 0.15 electron volt. This is the case for zero noise level. If you increase the noise, then this gets degraded a bit. Peak counts become, like, say, less efficient. The convolutional neural network is still, however, performing better. If your noise arrives to 70%, that's 70% of your noise, it's almost all noise, and you see that here it's basically just a random choice. There's no chance we can, I mean, there's a random chance to actually distinguish the true model. The convolutional neural network is still a little bit better than just a random chance. Finally, there's something that, again, of course, comes with the experiments and all the challenges which are related with it, from the technology to the systematics and to different observables. And this is something that in particular is very relevant within any probe, but I mean, in particular for me, I'm very much involved in the Euclid space mission. This is an ESA medium class space mission that was selected for the Cosmic Vision program, and that is expected to be launched at the end of next year. It's in particular also thanks to the great effort by Domenico Sapone in the audience, we validated the forecast pipeline, which is available in this paper. The Euclid will contain visible and infrared bands for 15,000 square degree sky coverage, and in particular will include two different complementary probes. That's actually the main property, let's say, of Euclid with respect to other surveys, and that we will include both weak lensing and galaxy clustering. And in fact, they depend in different ways on the expansion, on the growth of structure, and in particular on the perturbations, on the gravitational potentials. And so together, they can actually tell us a lot about the cosmology, and also about cosmology beyond the lambda CDM. It will include photometric data and spectroscopic data. These are some images of the actual instruments. This is the NISP, the Euclid Near-Infrared Spectrophotometer, that was delivered to ESA last year in May 2020. It's now wrapped like this. Inside, it actually looks like this. And this is the visible instrument, the VIS, that was also delivered to ESA in July last year. Then both of them are mounted on the Euclid payload module. This is the VIS, and here again, it's the NISP. There was a press release by ESA again in July 2020 about that. So I mentioned this paper, the validated forecast pipeline, because I think first, I mean, it was a lot of work, as Domenico can testify. And also because I think independently of whether you're working or not on Euclid, it can be useful if you're performing a forecast the point was that when we started, Domenico will remember, but we had many different codes, forecast codes that were actually predicting different things. All these contours were supposed to be overlapping in the sense that in principle, they were meant to be testing the same thing for the same model and for the same probes. And instead, we found out that there were lots of different codes around that were actually not matching, neither in the amplitude nor in the orientation of this of the constraints. And this is also what motivated then Euclid management to start this INTERSCIENCE task force that had to put together people with different expertise from different science working groups to agree on what to actually model, so on the recipe that had to model the equations for galaxy clustering, for weak lensing, and for their cross-correlation, take into account correctly the systematics for each probe, take into account a description of the nonlinear correction, which will be an approximation, but at least, again, it's the best approximation we could find so far. Identify perhaps an optimistic and pessimistic scenario to be more or less conservative, compare different codes implementing the same agreed recipe, and validate them. So arrive to a point in which they differ in the error of their errors in each of the parameters at less than 10% for each of the parameters. I think one of the main outcomes which can be useful again for the community is actually in the appendix, which may pass unnoticed, but that I want to again stress here because it illustrates how you can do your own code comparison. And it also includes a repository with all the reference matrices, also including the plotting routines for you to add the result of your own code within, for example, a plot like this, in which for each of the parameters, you can compare different outputs of different codes and see how much they differ and whether you have actually validated or not your own code. And then you can apply it to another experiment and again, you after you have validated it into a reference frame. Specifically for Euclid, this is the validated result. So after all this comparison, at the end, we finally made a plot of the different constraints expected from different probes, which also showed the importance of cross-correlation terms in the photometric part between weak lensing and photometric galaxy clustering that can improve the constraints, especially in parameters beyond lambda CDM, and the figure of merit of at least a factor of 3. So in conclusion, I hope I showed that there's lots of challenges which at the end, again, are part of this quest to understand what's in the universe and how it evolves. It usually starts with an idea, and then perhaps with a proposal to make an experiment to test this idea. This then, in turn, gives rise to a whole new set of challenges, the whole technological development, which can require, like in Euclid, 20 years to actually be put in place. There's then the whole data processing. So to reconstruct the actual, for example, shape of the galaxies that you actually see before, and the whole signal processing before you actually arrive to the final cosmological parameter. There's lots of choices involved in the statistics, in the systematics that of course have to be taken into account depending on the probe that you have. And some of these choices, again, may be optimized depending on what's the actual question that you want to answer. And after that, after this long process, after you've validated all the codes, you trust all these steps and you know what are the choices which are made in it, then you will arrive to a plot, the one that we see usually at the very end, in which you can test your theory and come up perhaps sometimes with a new idea and then a new experiment and start this all over. Or if you're lucky enough, perhaps get a chance to see some new fundamental physics. And I think I'll stop here. I don't see you, so I hope you're still there. And yeah, in case you want to ask questions, please.
Okay, thank you, Valeria. Very nice talk, and congratulations for all the work you have done and your very clear talk.